Hello and welcome. My name is Florian Pfaff and I'm from the Intelligent Sensor Actuator Systems Laboratory in Karlsruhe, Germany. The work is entitled Estimating Correlated Angles Using the Hypertoroidal Grid Filter, and it's about a novel grid filter which we compare with existing approaches. This work was done jointly with Kai-Lai Li and Uwe Hanebeck. We'll begin with a brief motivation about estimation on periodic manifolds. Periodic manifolds is that, as you can see in a circle, if you go around the manifold, you will arrive at the origin again. And there's also high dimensional versions, such as the hypertorus, where you have multiple ways to go along this, or the hypersphere, which is very different because it does not have a hole. So why is it tricky? If you have two measurements, one at 60 and one at 300 degrees, then taking the normal means would give 180 degrees, which is not what you want. You would want the 0 degrees here. So, and this is not just a theoretic problem. If you got the prior density with a mean at 60 degrees and likelihood with a mean at 300 degrees, then your Kalman filter will give you something with a mean at 180 degrees. However, this is not a problem of Bayes formula. If you apply Bayes formula, you will get something that has its mean, circular mean in this case, at 0 degrees. For all topologies just mentioned, filters have been proposed in the recent years. For the circle, there is the Fourier filter and a grid filter, which we call the Fourier interpolated grid filter, which is closely related to our novel approach. And there are a multitude of other filters that are, for example, assumed density filters that only consider a parametric form of densities. For the hypertorus, there is the hypertoroidal Fourier filter. This is also closely related to our novel approach. And for the hypersphere, we recently proposed the hyperspherical grid filter and the hyperhemispherical grid filter. With the insights to these grid filters, we wanted to develop a novel filter for the hypertorus. Why does it make sense to develop a new novel filter for the hypertorus? Well, for the Fourier filter, sophisticated modifications are necessary to ensure the non-negativity of the density that is approximated by the filter. And second, a grid filter may actually be more intuitive because the values at the grids may relate to the function values of the density. Lastly, the non-negativity is easier to maintain in this, as you will see in the coming slides. Before we get to our novel filters, we first give a brief overview over all filters for hypertoroidal domains. We now also illustrate how they represent densities. For this, we've shown here one density that is bimodal on the hypertorus. If you consider a bivariate normal filter, it can only consider univariate densities, which is why we only get a single mode here. It doesn't work for arbitrary dimensions. It can use almost arbitrary models with extensions for nonlinear models. It cannot account for multimodalities, but its runtime is, for being a bivariate filter, pretty decent. And it's more or less intuitive. It's somehow intuitive considering the densities, but it's less intuitive if you consider nonlinear extensions, which are a bit more sophisticated. Then there is the particle filter. The particle filter, the density is represented using multiple particles with certain weights, or they can also be unweighted, and then just the spacing encodes the actual density. It can be used for arbitrary dimensions, actually can be applied for almost all possible topologies. It supports arbitrary models, and multimodalities are no problem. As you can see here, we have some particles there, some particles there at the other mode. But its runtime, it actually works pretty good for low runtimes, but if you want a high accuracy, it converges really, really slowly. I would say it's also not perfectly intuitive. Then there's the Fourier filter, which, as you can see, represents this density pretty well. And it works for arbitrary dimensions in the hypertoroidal case. It can support arbitrary models. The multimodalities, as you can see, are encoded well. The runtime depends very much on the actual dimension. For high dimension, it gets pretty costly, but it's not that perfectly intuitive. So what we're now considering here is to find something that is actually more intuitive here. For a grid filter, we have to decide on what these grid values actually mean. There are two possible interpretations. First, they can describe the probability mass in the region. If we partition the domain into regions as thus, you see these pseudo-rectangular regions here, then the grid value would summarize all probability mass in that region. That can be obtained by an integral, which is typically costly, and what you would arrive at would be some kind of one-Helm filter, and to convert the models into the matrices needed for the one-Helm filter is also pretty costly since it involves multiple dimensional integrals for higher dimensions. Then the second interpretation that we focus on is that we say it's the function value of a continuous density at certain points. Well, for this you have to choose how are these points placed. You can place them equiangularly, so you see that there's a circle, there's a circle, there's a circle, there's a circle. So you have a grid on the rectangle 0 to pi, 0 to pi. We will consider that just in a minute. And you place them equidistantly in a regular grid. So you would have like squares on the rectangle, and then you have such shapes on the torus. Then there is a way to put a more homogeneous grid. This one was obtained via Lloyd's algorithm. So you maximize some distance between these points to cover it more uniformly, because here you would not have any information about what happens in this region, and you have a better coverage if you distribute them like that. So, but for our filter, we decide on this one. It does not cover it as well as good, but we obtain a very efficient prediction step for identity models with additive noise. So, but if we have something that encodes the function value of the density at certain points, we still need some form of interpolation if we want to have the continuous density at all points. One possibility is to interpolate it using a piecewise constant function, and we actually use this interpolation in our proof in the paper. But as you can see, this is not really continuous and doesn't look so pretty. It's much better to use a smooth interpolation via a trigonometric polynomial, which gives a pretty smooth density that looks like the original density. While the derivation given in the paper is for the piecewise constant function, you can always choose to interpolate the grid differently to obtain a different smooth function. Let's get to the implementation of Bayes' formula. We've got the grid values shown here according to the size of the circles of the prior density, which to visualize this is interpolated looks like that. And then we need the likelihood evaluated at the same grid points. Here also an interpolation that we'll never really need in practice. And that if we multiply them, we get the grid values of the unnormalized posterior density. Obviously, the non-negativity is maintained here because we just multiply non-negative values, and it's proportional to the true function values. What you have to keep in mind, however, is that if the density becomes more concentrated, then even if the likelihood is considered perfectly by the grid values, then you will lose some information here. This is like in the Fourier series. If you multiply two Fourier series with a specific number of coefficients, then you will need more Fourier coefficients to represent the multiplication result exactly. So you'll lose this increase in the complexity of the density. So let's get to the prediction step, and I'll briefly give the key ideas based on the one-dimensional case because it's much easier to visualize there. So we've got that posterior density from the last update step. It's just depending on one variable, but let's just say this is dependent on two variables. There's another variable of that future time step that our function is currently invariant under. And then we've got the transition density that is both variant on the current and the next time step. Then what this is here, this is just like a joint density that we obtain if we multiply these two functions. All we have to then do is perform this last step, the marginalization, to obtain the predicted density for the next time step. In the prediction step for identity models with additive noise, we use that the Chapman-Kolmogorov equation simplifies in this case because the transition density ft xt plus 1 xt then simply becomes fw, which is the density of the additive noise term of xt plus 1 minus xt. So if we have the vector of grid values gamma et from the previous update step, then we evaluate the noise density at the same grid points to obtain gamma w. Then to perform this efficiently, we reshape this into a tensor, a d-dimensional tensor, lambda e and lambda w. So to visualize this, lambda e would be really the ordered in this two-dimensional shape, because we are considering a two-dimensional density here, and the grid value is there. This would correspond to this density. For the noise density, same, we have them here on a grid, and we just take this as a matrix. The actual points, the grid points, do not matter. It's just that we have a matrix here, which corresponds to this density. And then we perform a cyclic convolution of these two matrices to obtain these grid values. And if you interpolate them, you get something that closely corresponds to the predicted density. Then you can reshape it for the next update step, but that's actually optional. If you only have prediction steps for identity model with additive noise, then you can just reformulate the update step based on the tensors, and you never have to return to the vector representation. In our evaluation, we compare the novel grid filter with other filters for hypertoroidal manifolds. We consider a three-dimensional scenario with a nonlinear system model, an identity measurement model, and both are perturbed by a noise term that is distributed according to a trivariate wrap normal distribution. Here we have the filter results. At the top we have the estimation error, which is the average of distance between the estimate at the last time step, that is determined as the circular mean, and the true value. And here we have the run times. So the particle filter converges slowly. You see with 2,500 particles, it has not reached the quality of the other filters, but for few particles, it's still pretty good. The grid filter already attains its optimal performance with 5 to the power of 3 grid points. You can see that here. And we believe that it's because the circular mean is already pretty close to the circular mean of the true posterior density, which is why it stops improving there. Then the grid filter is better than the Fourier square root filter. Slightly better here. It's actually comparable, I would say. It's identical here, but it's definitely faster, as you can see, as the Fourier square root filter. The Fourier identity filter, on the other hand, is much faster, but it's not as good as you can see here. Now, if we compare configurations of equal runtime, the grid filter is as good as the Fourier filter. As you can see here, let's compare these two configurations. These are of comparable runtime. then you can see that the filters are very close here. But one great advantage is that the grid filter ensures the non-negativity. So it should be preferred even if its estimation quality is equivalent for equal runtime. Finally, let's give a brief comparison with the Fourier filters. The approximation depends on whether a closed form solution for the Fourier coefficients is used for the Fourier filters. What you can see is that the Fourier identity filter here contains negative values, which is not very good. Then you've got the Fourier square root filter here, which is much better in that regard. It does not have any negative function values here. And then you've got the grid filter here. The grid filter actually has the disadvantage that it does not have the benefit of these explicit formulae, so it does not perfectly grasp that mean correctly. But this is just the approximation step once. So the update step of the grid filter is in O of n instead of O of n log n for the Fourier filters, and it avoids any risk of introducing negative values in the update step there. The prediction step for the identity model with additive noise for the grid filter is an n log n instead of O of n, but it's semantically equivalent to the one in the Fourier filter. Then the general prediction step of the grid filter introduces an error, while the one of the Fourier identity filter is error-free. But as we've seen in our evaluation, that's not that big of an issue. Then to summarize it up, we've presented a grid filter which is a very versatile filter for arbitrary models at arbitrary numbers of modes. And it has a fast prediction step that is made possible by its simple grid. And it's on par with the Fourier identity filter, but ensures the non-negativity of the density that is represented by the grid points. As an outlook, we could consider adaptive grids that change, so you can have higher resolution at points that are more interesting to us. Then we can also consider a Rao Blackwell-Lights filter to have combinations of periodic and linear manifolds. One very particular interesting thing would be to consider ones with spheres like SE3, and then to consider other domains such as disks. Here you can see that we would have to carefully consider how to design our grid. This is not equally dense everywhere, but maybe this has some advantage we would have to see there. And we could consider to use some of the insights of the grid filter and the Fourier filter to have something there that prevents non-negative values in some other way.
Then thank you for your attention, and I'm looking forward to seeing all of you in the special session on directional estimation, where I'll also be happy to answer all of your questions.